Hello students, welcome back to Vassiversity. Today we're going to be starting exponential functions and compounded interest. All right, so exponential functions. Let's go ahead and take a look at definition. So an exponential function is a function f is base a and it denoted as f of x equal to a to the power of x, where a is greater than 0 and a is not equal to 1. If it's equal to 1 to the power of x is just going to be 1. And x is any real number. Okay, so any real number. So let's take a look at some properties of exponential function. Okay, we can have our first rule is going to be, well, a to the power of 0, as long as a is greater than 0, right? It always will be equal to 1, right? And what's the reason behind it? Well, the reason behind it is essentially the 0th power is when we divide the two numbers with the same base, right? Because a is called base, right? Base a. So if we do a to the power of 2, let's say, divided by a to the power of 1, it's the same thing as a to the power of 2 minus 1, which is equal to a to the power of 1, which we call just a, right? Okay, so that leads us to a general rule, right? So rule 2 for addition, right? Addition of powers, so that means multiplication of the two exponential functions with the same base. So let's take a look. If we have a to the power of x times a to the power of y, right? So as long as the base is the same, we will have a to the power of x plus y, right? So we can add the powers. So that's why when we're working with a to the power of 2 times a to the power of 3, right? So same base, that's going to be a to the power of 2 plus 3, which is equal to a to the power of 5. Okay, perfect. Now, when we want to divide the two exponential numbers, we will have a to the power of x divided by a to the power of y. In this case, we are subtracting, right? So it's going to be a to the power of x minus y. So in this case, we can have an example of similarly as the previous one. So if we have a to the power of 3 divided by a to the power of 2, which is equal to a to the power of 3 minus 2 is equal to a to the power of 1, or just a. Okay, now that leads us to one of the interesting properties. So the negative exponents, because we can also have negative exponent. What if it was x was equal to 0, right? Then we would have a negative exponent. So let's take a look at it. So we can have a to the power of negative x, right? So what that means, it means that we had something like 1 over a to the x, right? And essentially, the reason why it's true is because, well, we can think of 1 as a to the 0. And if we think of it as a to the 0, what we can do? We can have 0 minus, essentially 0 minus x, which is negative x, right? So let's think about it this way. So a to the power of 0 divided by a to the power of x, which is equal to a to the power of 0 minus x, which is equal to a to the power of negative x, right? So we proved essentially that property. Okay, now let's go ahead and take a look at power to power, right? Because sometimes we might have something as the following. So we can have 5 a to the power of x and then to the power of y, right? So that is essentially going to be equal to a to the power of x times y. Okay, so it's going to be multiplication. So let's take a look at it. So if we have a to the power of 2 and then everything to the power of 3, so what does that actually mean, right? When we're having to the third power, we know that we can add. So if we have the same base, we're going to be able to add things. Okay, so that means here essentially we will have a squared to the power of 1, right, times a squared to the power of 1 times a squared to the power of 1, right? Everything here to the power of 1, but essentially we have the same base, so we can add the powers. So it's going to be a to the power of 2 plus 2 plus 2, right? This is repeating 3 times, right, because we have 3 terms. So that's going to be 2 plus 2, 4 plus 2, 6, so a to the power of 6. So and simply, it's the same thing as a 2 times 3. Okay, so we can prove that for n to the power of m, where it's x to the power of y, and where x and y are arbitrary. Okay, and then the last property for exponentials are going to be the root, right? So if we have a to the power of 1 over n, right? So now it's a fractional power for us. That is essentially taking a root. This is a root operation, so it's going to be the nth root of a, right? So when we are talking about a square root, right? A square root is going to be a to the power of 1/2. That's the same thing as square root of a, but we, for notation purposes, would not put the 2 here, right? It's implied every time that we have that this is a square root of the number. Okay, perfect. So as I previously said, we can have example for any real number, right? As long as a is not 0. And well, here we assume that a is positive, right? If a is negative, essentially we have to be careful because, well, if a is negative, if a is less than 0, right, what do we have? We essentially have, let's think of a to be positive, right? But we are going to multiply it by -1, right? So it's going to be something like negative a to the power of x. This is the same thing as -1 times a, everything to the power of x. So we can distribute the power, so it's going to be -1 to the power of x times a to the power of x. Right, so now here, actually, now I'm saying that a is positive, right, but that -1 is the tricky one because depending on the power of x, right, if it's an even power, it's going to be positive. If it's an odd power, it's going to be negative. So that's why we have to be careful because the sign of a to the x will change depending on the value of x. So here we have to be careful because sometimes we cannot really plot the negative the negative values based on if x is actually a variable here. So because if we have to fix x as not a variable, right? So x here is not a variable, something that we have to be careful about, because if we putting it to the power of negative power, it's not going to be functioning. So only works if we are working with a constant power, right? So just for computational purposes. Okay, so, and we'll label that it's not a function. And the reason why it's not a function is because, well, -1 to the power of x is simply an oscillating function. So we cannot really graph it. So the only point that actually would exist would when x is equal to 0, right? It would be true. All right, perfect. Now let's take a look at some examples. So we know the properties, and now we are going to be only assuming that a is positive, right? So a is positive, so we're going to have example 1, and we're going to have f of x is equal to 2 to the power of x, and g of x is equal to 4 to the power of x. Okay, so if we have x, right, let's go ahead and try to find some values. So we're going to have -3, -2, -1, 0, 1, 2. Okay, perfect. So let's see. And then we have f and g, right? So we're going to try to evaluate the f and g at those points, right? So what are we going to have? We're going to have for f of -3, right? F of -3, this is 2 to the -3. Same thing as 1 over 2 to the 3, which is equal to 1/8. Okay, how about the -2? So it's going to be 2 to the -2, which is equal to 1 over 2 to the 2. 2 to the 2, that's going to be 1/4. Okay, and then 2 to the -1, this is the same thing as 1 over 2. Pretty straightforward. To the 0, so anything to the 0 is going to be 1. 2 to the 1, that is 2. 2 to the 2, that is 4. How about g? For g, so we're going to have 4 to the -3 equal to 1 over 4 to the 3. So 4 to the 3, 4 times 4, that's 16. 16 times 4, that's 164. So 164. How about 4 to the -2? That is going to be 1 over 4 squared, which is equal to 1 over 16. How about -1? So it's going to be 4 to the -1, which is equal to 1/4. Okay, and then to the 0, once again, it's going to be just 1. Then 4 to the 1, that is 4. And 4 squared, that's going to be 16. Okay, so the functions are not too difficult, right? And let's actually go ahead and graph it, right? So I'm going to go ahead. This picture right here. So if we graph those two functions, that's how it's going to look like. Here we have the g of x equal to 4 to the power of x, right? So it's more steeper. It's growing faster, even though at the beginning, the 2 to the power of x is growing faster, right, in the beginning rate, right here if we zoom in. But as x approaches larger and larger number, 4 to the x is actually overtakes the 2 to the x and grows faster. Okay. Similarly, we will have the if we do the negative power, right? If we do the negative power, we will essentially the inverse the 2. So this is our graph. So let's go ahead and take a look at example 2. So I'm going to take the same functions, right? The same functions. Example 2, we're going to have f to the f of x is equal to 2 the negative x, and g of x is going to be equal to 4 to the negative x. Okay, so once again, let's make the table. So if we make the table here, we will have the following. So we're going to have same values, but let's actually make it -2, -1, 0, 1, 2, 3, right? So I increased the values purposely. And then here we're going to have the f, here we're going to have g, right? And we're going to be computing it as we go. So, okay, perfect. Let's go ahead and start. So we're going to have f of -2, right? So negative gives us positive. F, so it's going to be 2 of -2, that is positive, so that's equal to 2 to the 2, that's 4. 2 to the -1, that's 2 to the the positive 1, that is equal to 2. Okay, and then to the 0, that is always 1. Then to the power of 1, that's 2 to the -1, this is 1/2. 2 to the -2, so 2 to the -2, that is 1 over 2 to the 2, that is 4. And then 3, that's going to be 2 to the -3, which is equal to 1 over 2/3, which is equal to, so 2/3 is going to be 1/8, right? 2 times 2 times 2, that is 8. Okay, similarly, for the g function, right? So 4 to the -2, that is going to be just 16, right? Negative is positive. Then 4 to the -1, that's just gives us 4. And anything to the power of 0, so 4 to the power of 0, that's going to give us 1. Then 4 to the power 1, so it's going to be -1 here. It's going to be equal to 1 over 4. Then 4 to the power of -2, that is going to be 1 over 16. And 4 to the power of -3, that is equal to 1 over 4 to the power of 3, equal to 1 over 64. Right, similarly as we had in the previous problem, but now we're just reversing, right? Reversing essentially the table. And additionally, the graph is going to be reversed. Right, so now we're just reversing the graph as well. So now this is our g of x of 4 to the power of -x, right, decreasing like this, and 2 to the -x. So as we can see, the 4 to the -x is decreasing much more rapidly, especially it's approaching 0, right? It's reaching the 0 axis faster than 2 to the -x does, right? We can see here through the graph. All right, perfect. So here are some of the important parts about the functions, right? So about specifically exponential function. So let's take a look at it. So we can have, right? So the first we're going to be talking about the graph of y equal to a to the power of x, where a is greater than 1, right? So the domain is -infinity to positive infinity. The range is from 0 to positive infinity, right? We're never negative here in this. The y-intercept are always at 0, 1. It's increasing, right? Because it's positive and the power is positive. The value is positive. The power is also positive. There's no negative in front of it, so it's does not we're not enforcing any negative sign in front. So it's increasing from -infinity to positive infinity, and the x-axis is the horizontal asymptote, meaning that as x approaches -infinity, right? So as we going more and more negative to the left, right? So in this case, -infinity going this way, right? -infinity. Okay, and the function is continuous, right? So continuous, and later on in calculus we can learn what it means. But essentially, for this class, continuous means that we could draw it without lifting our hand, right? There is no sharp corners, there is no empty spots, there is no jumping, right, between one value to the other value, right? So that's what it means here. So now graph of y equal to a to the -x, where a is still greater than 1, right? Because we're only considering a to be positive and not equal to here. So the domain is -infinity to positive infinity, ranges from 0 to infinity. Y-intercept the same, 0, 1. It's now decreasing function, right? Because of that negative x, right? So we're forcing the values to be negative, so we flip the direction, essentially. So it's going to be the decreasing function, and x-axis is horizontal. Asymptote is as x approaches infinity, right? So here is positive infinity this way. So, okay. And it's also a continuous function, right? For the same reason as in the previous function. We can draw it without lifting our pen off the paper or plane. Okay, and now, of course, we can also do a translation of the function. So we can have following translation of the functions, and here in this example, we will have the following. So going to be our example 3, right? So we have 3 to the power of x, essentially. And so for part A, the graph essentially is obtained by shifting the f 1 to the left, right? That's what it means. We're shifting 1 to the left because if we put -1, now we're moving this point right here, right? So we shift it to the left if we add. Now, if we subtract from the function itself, right, we're subtracting not from the x, we're subtracting from the f of x, right? We're subtracting 2, so we're going down 2 units, right? We're shifting it 2 units down. Now, if we do 3x and -3x, we're essentially mirroring it all along the x-axis, and 3 to the x and 3 to the -x, we're mirroring along the y-axis here, right? And we have a common point right here. Here's this intersection. Okay, so we can do it for any kind of functions, any kind of base function. Essentially, that's going to be the same rules. Okay, now a very, very important number coming out from the exponential. So there is used to be a scientist called, his name was Leonhard Euler, and he created his constants called Euler constant, right? So the Euler constant is a very important mathematical constant, right? Which we learn in algebra and beginning of calculus, which is E, and it's equal to 2.7188828. Okay, and right, essentially, it's irrational number here. It's not we cannot express it as a fraction, but it has its own notation here, and it is very, very special number. We call it a natural base, right? This is a natural base, and it's called a natural exponential function. So f of x is equal to e to the x. We call it natural exponential function, right? One of the very important functions in mathematics. So a graph of this function essentially doesn't really look much different to the other ones, right? It's just now the values are one comma e to the -1. We just get to remember that it's this number, right? We remember the first 3 digits, right? 2.718. That's going to be good enough to remember, right? And it's used in a lot of applications, right? We're not going to give a proof here of how that number came along. That's going to be in the calculus series for Vassiversity. So stay tuned, and you will be able to find the link in the description for the proof of this constant. Meanwhile, one of the interesting applications that that number is arrived is specifically in compounded interest, right? So a compounded interest is going to be as following. So compounded interest, and so every time we're dealing with some bank account, right? We have a balance on the account, and we have some principal, which is the original deposit, annual, and we want to deposit some money into the bank under some sort of interest rate or like annual interest rate, and we want to know how much money we'll have in the future after some amount of years going to pass. The formula is going to be as following. So the amount is equal to the deposit, which is, we call it principal, times 1 plus the rate that we're given, divided by the number of times, or the number of compoundings per year we're doing. So to the power of n times t, right? Number of years times number of times we make payments, right? If we're just doing yearly payment, essentially n is going to be 1. If we're depositing money every year, let's say at the end of the year, then we're going to get the how much the rate is given by the bank. Okay, so essentially A is the bounce, P is the deposit, so original deposit, right? Then R is the annual interest rate. Okay, and then N is number of compoundings per year. Okay. And then we also have time, right? So t is going to be time in years, right? So t, that's going to be time in years in this case. Okay, perfect. So essentially, if we have a pattern, right? So if we want to do it for many, many, many years, essentially we can think about it. We can develop that formula for the following manner. So we can say, well, okay, at year 0, we have the original payment and we decide to deposit it, right? At the end of the year, so the new year begins and we are going to get the full interest. So that's going to be the full interest. Then we're going to, at the end of the year, we're going to deposit again the amount. So it's going to be the P1, which is that money that we had from the last year plus the new year. So essentially, that's how it's going to be squared of the original, right? This is how much time. So there's a 2-year past, 3-year past, and then T amount of year past if we're doing just a yearly compound interest. Okay, so what we can do is essentially we're just gonna, if we are doing this following continuous compound interest, right? So continuously meaning that we are compounding every second, right? And let's try to think the following way. So we have the formula, right? We have the formula A is equal to P1 plus R over N and T. And so, well, now let's substitute that formula in that formula the following. So we're going to say let M to be N over R. Okay, and that will lead us to be P1 plus R divided by, we're going to say MR. Okay, and then to the power of MRT. So M times R times. Okay, so now R and R cancels out, right? We can see that here. R and R cancels out. So what are we going to have is going to be E1 plus 1 over M to the power of M times R times T. Okay, so by the properties of exponents, we're going to have P times 1. So I'm going to put double parenthesis 1 plus 1 over M to the power of M, and then to the power of RT. Right, where I'm just separated it by the property. So we're interested specifically in this middle piece right here. So later on, we're gonna learn, and we're not gonna give any details here. As I said, you're gonna find the link below. But essentially, as we grow this number, and as M grows, so this expression here gets to E, right? Gets to E. Meanwhile, so that means this in the middle part is growing to E, so we're going to have that it's the same thing as P times E to the power of RT, right? This is a natural base, and that's essentially, in a very similar fashion, that's how Leonhard Euler found that number, and he called it the Euler's constant. Okay, so the useful formulas to remember for compound interest rates, right? If you want to calculate, you can do this following notes here. So we can use either compounding interest, which is more realistic. Meanwhile, for continuous compounding, which is the perfect case, this is a perfect case. This is impossible to achieve in real life. This is a mathematical perfect case. This is the more realistic compounding interest rate because it gets compound not instantly, essentially, right? We can do it quarterly. We can do it monthly. We can do it yearly. We can do it daily if we really want to. But we cannot do it instantaneously or, as we could say, continuously. Okay, so here we can say we can take a look at the following problem, right? So we wanna invest $12,000 at the annual rate of 3% and find the balance after 5 years for each type of compounding, quarterly, monthly, and continuously. So for part A, we want to do it quarterly, right? So in a year, how many quarters do we have in a year? 4 quarters. So n is equal to 4, and we want to have time to be 5 years. Interest annual rate is equal to 3%, or the same thing as 0. We can do it, right? 3% is 3 divided by 100, which is equal to 0.03. Okay, so that means our amount is going to be 12,000. This is our initial deposit. 1 plus 0.03 divided by 4 to the power of 4 times 5. So if we plug that into the calculator, we're going to get $13,954.21. Okay, now for part B, we want to do it monthly. So same idea. So we're going to have n to be equal to 12, right? The rest of the numbers are the same. So because we have t equal to 5, everything is same, but now a is going to be equal to 12,000 times 1 plus 0.03 divided by 12 to the power of 12 times 5. So that will give us 13,959.40. And then if we do it continuously, right, the perfect case for this problem, the perfect case, that's the maximum amount of money. So it's going to be A is equal to 12,000 times E to the power, right, to the power of RT, which is 0.03 times 5. That's perfect case. And that will give us $13,942.01. Okay, so essentially, if we decide to do it quarterly, we lose essentially $8, right? Even less, $7.90, 80 cents. $7.80, right? This is the net loss between this case and this case. It's gonna be $7.80, right? This is how much we would lose essentially, right? Comparing continuous to quarterly. All right, perfect. So next time we're going to be talking about logarithms, which is inverse of the exponential function. See you soon next time. See you guys later. Thank you for watching. See you next lesson. Thank you for watching. See you next lesson.